To our exclusive physics interview with scientist Terryn Brunelle. In this segment, Terryn will be talking with us about velocity and acceleration. Let's start with the first question. How can one tell the difference between distance and displacement?
Interesting question. Let's think of an ant traveling along a straight path. The distance the ant travels would be simply how many meters it actually walks, while the ant's displacement would be how much it changes its position.
So, are there any ways to tell how fast the ant is actually moving?
Yes. Imagine the ant travels 1 meter into a person's home, but quickly skitters back outside after seeing a cat. The ant travels a distance of 2 meters, but its displacement is only 0 meters because it returned to its original position. The velocity of the ant represents the rate at which it changed its position. If the ant takes 1 second to enter the home and 1 second to leave, the ant's velocity was 1 meter per second into the home, 1 meter per second out of the home, and 0 meters per second overall.
But wouldn't it be more realistic if the ant traveled faster out of the home than into it, especially since it was being chased by the cat?
Most likely. In this case, the ant would be undergoing acceleration, which represents a change in velocity.
So if the ant were accelerating, its final velocity would be different from its initial velocity, right?
Correct. We can use the kinematics equations to solve this problem. If the ant is at rest 1 meter inside the house, sees a cat, and skitters out with an acceleration of 0.5 meters per second squared, the ant's velocity, by the time it reaches the outside, would be the square root of 0 plus 2 times 1 times 0.5, which is equal to 1 meter per second.
Very interesting. So we have talked a lot about horizontal velocity and acceleration, but can similar movement occur in the vertical direction as well?
Yes, and this question brings me to the ideas of freefall and projectile motion. Simply dropping this stuffed animal on the floor represents freefall, which is the same as movement on the x-axis, except for that it occurs on the y-axis and acceleration is caused by gravity.
Vertical movement together.
If we launch this stuffed animal out horizontally, the animal falls along a curvature. We still have vertical acceleration of negative 9.8 meters to the second squared, but we now have a constant horizontal velocity as well. If we instead launch the stuffed animal at an angle, we still have vertical acceleration of negative 9.8 meters per second squared, but now we also have initial vertical velocity due to our launch angle, in addition to the constant horizontal velocity. Welcome back. Today we have an exclusive interview with Kristyn Demers.
Thank you for having me.
So Kristyn, can you describe for our viewers Newton's laws?
Absolutely. Sir Isaac Newton is credited with creating 3 laws of motion. The first, known as the law of inertia, is an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an outside force. An example of this would be if you kicked a ball in space. The ball would never stop unless it hit an object.
Oh, that makes sense since there's no gravity, friction, or air resistance in space.
Exactly. Now the second law of motion states that force is proportional to mass and acceleration. This can be seen with the equation force equals mass times acceleration. It would be easier to push an empty shopping cart instead of a full one, right?
Right, because the empty shopping cart has less mass.
Precisely. That's what Newton's second law is all about. Now the final law, the third one, states that for every action there is an equal and opposite reaction. An example could be a gun recoiling after it has been fired.
Okay, great. Moving on to the different types of forces, we have 5 forces we will be discussing. First, we have friction. That's something we experience every day, right?
Yes, if you ever shuffle your feet on a carpet and you feel the heat that is created, it is simply a byproduct of friction. The force of friction, which opposes the normal force, actually has 2 different types as well. Kinetic friction is the force that opposes the motion of 2 touching objects that are moving. Static friction keeps objects from moving. This is experienced when you push against a table but it doesn't move. But there's a force that's more common than that.
Really? What is it?
Well, the force of gravity is actually a key component to our lives. Without it, we would float around like astronauts. It is plainly the force applied on an object by gravity.
Huh. Yeah, life would be pretty difficult if there was no gravity. What's another common force?
The normal force is the force applied by one object to another. So if you placed a book on a table, there is a normal force between the table and the book, so that the book doesn't go through the table. A fourth common force is the applied force, where the force is being applied to another object.
Very interesting. Now tell me a little bit about tension.
I don't feel any tension between us, do you?
No, not that kind of tension. The force of tension.
Oh, yeah. So the force of tension occurs whenever there is a string or rope being pulled tight by forces acting on both ends.
Switching gears a little bit, can we talk about energy?
Of course, and that was the perfect transition because we can talk about mechanical energy. Get it? Gears, mechanics. Anyways, mechanical energy is the energy of motion and the position of objects, and it is made up of two different types of energy. Kinetic energy, one of these types, is the energy of motion. Potential energy, the second component, is often referred to as stored energy.
Get your Schrodinger's cat today. It's always a surprise, whether he's dead or alive.
Accelerate your delivery from a small express fee of $9.80. So Terryn, what is it like to work as a physicist?
Well, I don't really have to do a lot of work for my job. I'm pretty stationary, so a lot of times I'm not doing any work at all.
But surely...
Oh, sorry. I thought you were referring to physics-based work. In physics, work is the product of a force and the displacement over which the force is exerted.
Oh, you see, the concept of modern-day working seems the complete opposite of work in physics then.
Indeed. This cat has the ability to do a lot of work, but is only willing to raise his arm slightly to high-five me. The work done by the cat's arm equals the distance it is raised times the force the cat exerts on it.
That's probably the reason it's harder to train cats than dogs. Cats are less inclined to do the work.
Yes, and dogs likely also have a higher power rating than cats. Having more power means that the dog can do work in a faster amount of time. Cats and dogs probably have about the same power rating for doing a high five, but when it comes to sled racing, a dog has a lot more power than a cat.
So what if I train my dog to push open the front door? He's doing work, right?
Yes. It actually takes torque for the dog to open the door because the door is rotating on its hinge. The torque required is equal to the force the dog exerts on the door multiplied by the perpendicular distance between the force's line of action and the center of rotation.
But what if the torque is determined by two vectors on separate axes?
Then we can use the right-hand rule to determine the direction of the resultant vector. For example, using the hand curl method, we place our pinky's hand side on the first vector, we curl our fingers in direction of the second vector, and we stick our thumb out to find the direction of the resultant vector. We can also use the three-finger method. We point our thumb in the direction of the first vector, our pointer in the direction of the second, and stick out our middle finger to show where the direction of the resultant is. Kristyn, can you explain impulse for us? And not the impulse we experience while shopping, but rather the one that relates to physics.
Sure. Impulse is the change in momentum. We recognize in the impulse momentum theorem that this change takes force in time. Therefore, impulse has a time and a force component, which explains why the units are Newton seconds.
And what exactly is momentum?
Momentum is a mass in motion and is measured in kilogram meters per second. Again, the units really make sense as the mass correlates with the kilograms and the motion or velocity correlates with the meters per second.
Now, with momentum, we can study the different types of collisions. What are they and what makes them different?
Well, elastic collisions occur when two objects collide but then move off separately. In this type of collision, there is no change in the total amount of kinetic energy. However, in inelastic collisions, when two objects collide, fuse into one mass, and move together in the same direction, some kinetic energy is lost to heat and sound.
Well, that's all we have time for now. As always, Kristyn, it's a pleasure having you as a guest.
Yes, well, thank you for having me.
We'll see you in a little bit.
Welcome to our final segment. I know that we have talked a lot about linear and planar motion, but are there any other types of motion you care to share your thoughts about? Like when I'm driving around a curve in my car.
You're referring to rotational motion. The rate at which your car rotates around the curve is its angular velocity.
So turning is just the same as driving straight, except the velocity is angular instead of linear?
Yes and no. The car experiences centripetal acceleration directed towards the center of its circular path, pulling the object towards the center of the circle. This force results from things such as tension, gravity, or in your car's case, friction.
But wait, if a rotating object always has a centripetal acceleration, can it never move at a constant speed?
Actually, the magnitude of the object's velocity can be constant. The centripetal force causes the velocity's direction to change, resulting in a circular path.
That makes sense, but what about the force I feel when I'm pushed out towards the side of the car? Shouldn't I actually be pulled towards the inside?
You are pushed out due to the centrifugal force, which isn't actually a force, but a result of your body's inertia. Your body wants to continue moving at its current velocity, so the car turning causes you to be pushed outwards because your body is trying to fly off the circular path.
So you do have a linear velocity while you're rotating?
Yes, this is called your tangential velocity, and is how fast an object would travel if it were released from its circular path. This cat toy has a constant angular velocity. If I let go of the toy, releasing tension in the rope, and thus nullifying the centripetal force, the toy flings off the circular path and travels at its tangential velocity.
Oh, that's really cool. Well, thank you, Terryn, for your interview. We hope that you've enjoyed this video. Is there anything else you'd like to add?
Just one thing. If anyone sees Schrodinger, tell him we have a question for him. We haven't seen that cat that was on earlier in a while, and we need to know if he's dead or alive.